Welcome to the GeoMethod channel. Today we are solving another interesting geometry problem. Here is today's challenge. Can you find the semicircle area? Take a moment to study the figure. Then let us uncover the key geometric ideas that make the solution click. Here is a green semicircle resting on the diameter segment AB, with center O at its midpoint. Our whole job is to find the area of this green region, and the area of any semicircle needs just one number, its radius. The semicircle area is 1/2 pi times the radius squared. So instead of chasing the radius itself, we only need to pin down r squared, which we will build from two clean relations. A slanted chord runs from C on the arc across to the diameter end B. A point P cuts this chord into a right-hand piece segment, CP, of length 2, and a left-hand piece segment, PB, of length 3. That split point P is special because it also lies on the horizontal radius through the center O. P is exactly where the slanted chord crosses that horizontal line, and that overlap is what links the two chords. Let the distance from the center O out to P be P. The full horizontal radius OD has length r, so P sits on that radius a distance P to the right of the center. The radius OD extends straight to the right from the diameter, so it meets segment AB at a right angle at O. Hold on to that right angle, we will use it a little later. To use crossing chords, I need a full chord, so continue the horizontal line straight to the left, past the center to the left side of the full circle, and mark that point E. Now draw the whole horizontal chord from D through P to E. Measuring from P, the right-hand piece out to D is R minus P, and the left-hand piece out to E is R plus P, because E sits a full radius to the left of the center. Those are the two pieces of the horizontal chord at P. Our first insight is this: intersecting chords gives a difference of squares. The left side is easy, 2 times 3, which is 6. That is the product coming from the slanted chord. The right side is r minus p times r plus p. That is the product from the horizontal chord, still carrying our two unknowns, r and p. That product is a difference of squares, so it collapses neatly to r squared minus p squared. The two middle terms cancel, and nothing else survives. Setting the two sides equal gives our first relation, r squared minus p squared equals 6. Keep it aside. We still need a second equation to separate r squared from p squared. Now look at triangle OPB. The side OB lies along the diameter, and segment OP extends straight to the right, so the angle at O is the right angle we noticed earlier. Its two legs are segment OB, the radius r, and segment OP, the length p. The hypotenuse is segment PB, which the problem tells us has length 3. By the Pythagorean theorem, the hypotenuse squared equals the sum of the leg squares, so segment PB squared equals r squared plus p squared. Put in segment PB equals 3, so 3 squared, which is 9, equals r squared plus p squared. That is our second relation. R squared plus p squared equals 9. Now we hold two equations in r squared and p squared ready to combine. A second insight now finishes the structure. Adding the two relations eliminates p. What remains is 2r squared equals 15. The length p has vanished completely, which is exactly what we were hoping for. Divide both sides by 2, so r squared is 15 over 2. And notice the area only needs r squared, so there is no square root to take. There is also a shorter confirmation. Triangles ABC and PBO are similar because both are right triangles and they share angle B. Corresponding sides give 3 over r equals 2r over 5, so r squared is 15 over 2. Therefore, the semicircle area is 15 pi over 4. That completes the solution. A good geometry problem often has more than one beautiful solution. If you see a genuinely different construction, a high-level idea that leads to another solution, or a thoughtful adaptation of an existing method, share it in the comments. Even a rough idea is welcome. A sketch of the key move is enough. We greatly appreciate these contributions. With your permission, we may feature the approach in a future Viewer Solutions episode and acknowledge you by name or channel handle. Thanks for exploring geometry with GeoMethod.